Hello, calculus students. Welcome to another online lesson. Today, we are going to continue our discussion on integrals and specifically talk about finding the area between curves or between functions. And this is where things start to get interesting because now it's not just some shape like, let's say, a parabola that's bordered by the x-axis, but it can be a shape like a parabola bordered by a sine function, or it could be a parabola bordered by a line that cuts it like that. So we would have just that shaded region or things like that. So now we can really start getting interesting with our areas and our shapes that we're creating with our functions. We're going between curves. So if two functions f of x and g of x intersect at an x value of a and an x value of b, and f of x is greater than or equal to g of x for all x in the interval from a to b of x, regardless of the position of the x-axis, then the area under the shaded region between their points of intersection is given by the following function. So let's cut through what was being said there. So two functions, f of x and g of x. So I'm going to let f of x actually be my red function for a second. So we have this function here on the picture that I'm now outlining in red. And then I'm going to let g of x be my green circle. And so I'm outlining on the graph now, the picture, in green there. And you can see that those two things enclose a shaded region. They actually enclose several shaded regions, to be completely honest. There's another shaded region, or we could make another shaded region over here as well. But if I want to find just this enclosed region, I simply need to know the x values where they intersect. And I also need to make sure that the function that is on top goes first, and the function that is on the bottom goes second here in my function. And then again, just like before, we have an interval from A to B. So that's what we're talking about here. We can see our intervals A and B there. We simply subtract our functions. As we know from our rules of integration or properties, we could also turn this into from A to B of f of x dx minus the integral from A to B of g of x dx. And that would give us the same answer. These guys are equivalent. But again, you have to check to make sure which function is on top. Otherwise, you will end up with a negative area. So it's not the end of the world if you don't do it, but that's what we're looking for here. All right. So let's find the area enclosed by the region y equals x plus 2 and y equals x squared plus x minus 2. Because it says enclosed, we should be able to sort of, cap them off, if you will. They will create a region that doesn't have any gaps. Now, to start with, we have a parabola, and I could get that into vertex form, but I'm just going to rough estimate it here and say that I've got some sort of parabola, and then I've also got some sort of line happening here, which is y equals x plus 2, which would have a positive y-intercept and a slope of 1, so it would look something like this. Now, this is not to scale. Again, my function y equals x squared plus x minus 2 that I did in green, I'm not sure how accurate that is. But I'm looking for the two spots where these things intersect. If I call this first one the x value a and this one b, those are going to go in my integral as a and b. So I need to find out where my graphs intersect first to find out how far to go on my integral. So how do we find out where graphs intersect? We set them equal to each other. So let's set x plus 2 equal to x squared plus x minus 2. I'm going to get all my x's to one side. I'm going to get everything to one side, in fact. So I'm going to subtract x and subtract 2. So minus x minus 2. These cancel out, leaving 0. So I get x squared. These x's cancel out as well, which makes this problem very nice. And I get x squared minus 4. So now I have x squared. I add 4 to both sides, square root both sides. I wrote that square root, so there are two solutions, positive and negative 2. So for my integral, I am going to be going from from negative to positive 2. That's what we found out there. By setting those two equations equal, we now find out where they intersect, and so where the borders of our enclosed region are. We also know, as I showed with that picture, that this function is going to be the one that's on top. Again, if we have a parabola, we have this line crossing through, it's the line that will be on top. So that becomes like my f of x, and this is like my g of x. And I'm going to subtract. So I'm going to do the integral from negative 2 of this first function, which is x plus 2, minus the second function, which is x squared plus x minus 2, all in terms of x. Now you could just break these up into two functions as I showed, but there's a lot of like terms here. So what I'm going to do is I'm actually going to just make one big old function. And so combining terms, these are all going to become negative, or switch signs at least. And so I will end up with an x. And over here, this guy's going to be a negative x. Maybe I should write this all out. So I'll have x plus 2, then minus x squared, minus x, and plus 2. And again, that's after distributing those negatives, all dx. Now we can combine some terms. We end up with these guys canceling out. And so I have from negative 2 to 2, the integral of negative x squared, which is right here, plus 4 dx. Now I'm going to actually do the integral, or the antiderivative. And so I end up with negative 2, x to the third, and I divide the 3, so I have negative 2/3 x to the third plus 4x, all going from negative 2 to positive 2. Now I'm going to sort of use my fundamental theorem of calculus here, and I'm going to plug in my upper bound, which is a positive 2. So I have negative 2/3 times 2 to the third plus 4 times 2. I'll switch colors here to try to make things easier, minus the same exact thing. So I'm going to use a big old set of parentheses, or I could use brackets here, of negative 2/3 negative 2 cubed plus 4 times negative 2. So that's my function there. Now, as I start simplifying, I'll have negative 2/3 here. 2 to the third power is 8, plus 4 times 2, which is also 8. Now I need to distribute this negative in here. We'll get to each one of those. And so it's going to become a positive 2/3. And then I've got negative 2/3 to the third power, which becomes a negative 8. And then I had this 4 times negative 2 here, which becomes negative 8, but I'm distributing a negative, so it becomes a positive 8. So what do we notice here? I now have negative 16/3 plus 8 minus 16/3 again plus 8. So it's basically the same expression twice. So I just need to double it. But in order to combine these like terms, I need to get a common denominator. So I'm going to make this 8/1, multiply both the top and the bottom by 3. And I can do that over here as well. So I end up with negative 16/3 plus 24/3. And minus 16/3 again, plus 24/3 again. 24 minus 16 gives me 8/3. And I have another 8/3 right here, which leaves me with 16 thirds units squared, and that is my area between the regions. So what are we doing here? We're applying our fundamental theorem of calculus, but we're first have to figure out where our boundaries are. We found the boundaries by setting the two equations equal to find out where they intersect. We had to decide which equation was on top, which equation was on the bottom. We set those up as our f and g of x. We combined the function, simplified everything, did our integral, plugged in our values, simplified, and that gave us our answer. The second example in the slideshow we will look at in class next time. In the meantime, we have some problems we can take a look at on page 481.